Greetings and welcome to our presentation entitled Robust Tracking Control of Mechanical Hybrid Systems Driven by Electrical Actuators. The outline of the presentation is as follows. First, we would like to give an introduction. Then, we will show our main results. After that, we will provide some experimental results. And finally, some conclusions. The introduction first. It's quite common to compute torque forces to achieve the control of hybrid mechanical systems. However, the control inputs of mechanical systems are frequently produced through voltage applied to electrical actuators, which in turn generate the torque forces. In this work, we complement existing literature by considering the additional dynamics corresponding to electrical actuators. Therefore, we synthesize voltages rather than torque forces to control mechanical systems in the presence of unilateral position constraints. Now we would like to show our main results. Let's start by the problem description. Consider a neural Lagrangian actuator dynamics along a unilateral constraint F0 depending on position, which is greater than 0. When this is the case, then our dynamics is given by these equations, where here we have the system dynamics and here we have the actuator dynamics. Then, when the unilateral constraint is in place, position, velocity, and torque satisfies these equations, where the new introduced variables W, Q, W, tau, and capital W are perturbations, and nu is the control input to be designed. In the same spirit, the reference trajectory is defined by Q star and dot Q star, and is subject to collisions with the continuous dynamics when the system is outside the unilateral constraint, and satisfies these equations when the reference position and velocity satisfies this unilateral constraint. We assume that the reference and the hybrid system trajectories hit respectively the surfaces defined for each one at the same time instant. For the controller synthesis, we divide this in three main steps. First, we present the continuous aerodynamics. Then we introduce the errors at the collision instance. And finally, we design the control input nu as a function of an auxiliary control input eta and the torque. This is based on the H-infinity control theory. Let us start by the first step, presenting the continuous aerodynamics. In this case, we define the position and velocity error variables, like we can see here. IP is position error variable, and IV is the velocity error variable. Then the continuous dynamics, this means dynamics when the system is outside the unilateral constraint, is given in this form. Choose tau as in equation 2, where U is a new virtual variable. Notice that tau as in 2 warrants an equilibrium at the origin of the unforced system 1. This means when tau and WQ are equal to 0. From tau, given by this equation, we can isolate the new virtual variable U as shown here. This new virtual variable U represents the torque error. Taking its time derivative and using the dynamics of the actuator, yield these dynamics that we're presenting here, where notice that here appears the voltage control input nu that must be designed. In turn, substituting nu equals this right-hand side into this equation 3 yields this dynamics, where eta is a virtual control variable to be designed. Once we have eta, we have completely defined nu, which is our voltage control input. We would like to continue by introducing the errors at the collision instance. Position and velocity errors at the collision instance are given by these equations that we are showing here. And the torque does not change during collisions. Therefore, it's straightforward to get this equation here, where W1D and W2D are inherent perturbations. Now we would like to summarize steps 1 and 2. From the first step, continuous dynamics is obtained and is shown in these equations here, where the states position error, velocity error, and the virtual variable u, and the reference position q star, velocity q dot star, and acceleration dot q star are available for the virtual control eta design. Finally, remember that our voltage input is designed as shown in this equation, where the new virtual control variable eta must be designed. From step 2, we get the transitions in the states at the collision instance, as given in these equations here, where one more time, capital W1D and capital W2D are inherent perturbations. And finally, the third step, which is the design of nu as a function of the virtual control variable eta and the torque. We used in this case H infinity control theory. We base our design of the virtual control eta on previous results in H infinity synthesis for hybrid systems from Montano, Orloff, and Austin in 2014. To do so, let us introduce the state variable E and its continuous dynamics as shown here, with a transition stage given by these equations, where CIT and CITEDI are performance outputs. The functions h1 and k12 are assumed to obey the well-known assumptions shown in 4, which are typically used in the traditional H infinity synthesis design. See, for example, Isidori and Stolfi 1992. This H infinity control problem has a global solution. Consider the causal feedback controller eta as a function xi of the state vector E, where this function xi is continuous differentiable at least one time, and xi at 0 is equal to 0. Controller 5 is said to be a locally global admissible controller if the undisturbed, in this case all perturbations must be equal to 0, closed-loop hybrid system in terms of errors is uniformly globally asymptotically stable. The problem then consists in finding an admissible global controller 5, if any, such that the L2 gain of a disturbed hybrid system satisfies this inequality presented here for some positive definitive functions beta 0 until beta n capital N for all segments between T0 and capital T, and a natural capital N sub capital T such that this restriction is fulfilled, and for all piecewise continuous disturbances W and discrete ones capital W. This H infinity control problem has also a local solution. Conditions must be satisfied in order to this local solution to be found. Let's start by the first condition, C1. There exists epsilon 0 greater than 0 such that this differential Riccati equation has a uniformly bounded solution P epsilon, positive a definite solution for each epsilon contained in this interval. The second condition, the norm of the matrix function W is upper bounded by this quantity, which means that this inequality must be fulfilled. The third condition, there exists a smooth, positive, definite decreasing function V and a positive definite function R such that the Hamilton-Jacobi-Isaacs inequality presented here holds with alpha 1 and alpha 2 as given here. The fourth condition, condition 3 is satisfied with V that decreases along the direction mu in the sense that the inequality shown here holds in the domain of V. Now we can state the theorem that solves this H-infinity contour problem. Let condition C1 be satisfied with some gamma, positive gamma, for the aerodynamics of the mechanical hybrid system driven by actuators that we have shown before. Then condition C3 holds locally around the equilibrium E equal 0 of this dynamics with V as given here, R as given here, and the closed loop system driven by the state feedback eta as shown in 7 locally possesses a L2 gain less than gamma, provided that the condition C2 holds as well. If, in addition, the condition C4 is satisfied with the quadratic function V given in 6, given here, then the disturbance-free closed loop with 7 is uniformly asymptotically stable. Now that we have presented the solution to the control of a hybrid mechanical system with unilateral constraints, we are in place to give our experimental results. The experimental setup consists of this simple pendulum and this unilateral constraint. The system hits this constraint as it's shown here in this diagram. We have a barrier, we have the origin in the upper part of the system, and the dynamics is described by position, velocity of the pendulum. The reference trajectory is given by the hybrid van der Poel oscillator. Given the set S, the hybrid oscillator is given by the continuous dynamics as shown here outside this set, and by the transitions shown here when the system is inside the set. With this T sub E impact instance. A discontinuous limit cycle is generated if alpha equal mu equal 1 in these equations, rho equal 1.5 and kappa equal 0.5. As you can see here in this figure, this is the velocity versus position phase plane. And in this figure here, we shows the phase portrait after the transient, where the position of the pendulum is initialized at downward position equals p radians, and its velocity equals 0, it's stopped. The torque generated by the motor is given in this figure, where we show here saturation limits. And in this figure, we show our control input voltage, which is inside the saturation area. It means maximum value 0.8, minimum value minus 0.8. We would like to show next a video of this experiment.
Yeah.
Finally, we would like to present our conclusion. A robust tracking controller was designed for a hybrid air-orange system driven by an electrical actuator. Although an intermittent perturbation was unavoidable in the transition stage of the aerodynamics, we achieved robust tracking with an appropriate disturbance attenuation level. The experimental results corroborated the theoretical development given in this presentation. Thank you so much for your attention, and here at the bottom of the presentation we left some contact information.